After studying this module, you shall be able to learn the concept of chi-square, learn to make inferences about frequencies, and identify the assumptions of chi-square. Some of the previous modules were concerned with scores on one or more variables and using these scores to make inferences about population means. This module is mainly concerned about making inferences about frequencies, the number of individuals falling under different categories of frequency distributions. Many a times in research, the need to test experimentally observed results against the direct determination of probable outcomes is desired. Let us think of an experimental situation where the psychologist wishes to study two tones which differ slightly in their pitch. The subject's task is to compare the two tones which are to be presented in succession and give the response for the second tone to be higher or lower in pitch when compared to the first. Of course, the presentation would be done randomly and repeated number of times. The data is recorded as the subject being right or wrong and the responses are independent of each other. The experimental results obtained here may not result in a normal distribution and therefore its application would not be advised. Under such conditions, direct calculation of probabilities is a better idea. So when the data are badly skewed, sample size is very small and the assumption of normalcy is questionable, the parametric methods are not applied. In such situations, distribution-free methods or the non-parametric methods are more useful. The non-parametric tests are used when the sample size is small, assumptions of normalcy about the population is doubtful, and the data is in lower scales of measurement. When the collected data is in the basic scale of measurement, that is nominal or ordinal, and the researcher wishes to see a pattern of results with respect to observed and expected data, the chi-square test may be used. The chi-square test. The chi-square test was introduced by Carl Pearson in 1900. It is the discrepancy between the observed frequencies, the frequencies that are actually obtained from a random sample, and the expected frequencies, the frequencies expected according to hypothesis of nominal variables, in which subjects are grouped in categories or cells. It proves especially useful in conditions that require comparing empirically obtained results with the theoretically expected results on some hypothesis. There are two basic types of chi-square analysis: the goodness of fit test used with a single nominal variable and the test of independence used with two nominal variables. Both types of chi-square use the same formula. The general formula for chi-square is chi-square is equal to sigma FO minus FE whole square upon FE, where FO is the observed frequency, FE is the expected frequency, and thus the value of chi-square equals the sum of observed minus expected difference squared and divided by expected frequency. The more the observed frequency differs from the expected frequency, the larger is the chi-square. When chi-square values exceed the appropriate critical value, it is declared significant, and the chi-square is used on variables that are measured on nominal and ordinal data. Although the chi-square test is popularly conducted in terms of frequencies, it is best viewed as a test about proportions. The calculated value of chi-square can be evaluated with the appropriate degrees of freedom. df is equal to r minus 1 into c minus 1, where r stands for rows and c for columns in the data table, for the chi-square table to make inferences about the hypothesis. We shall explain this by taking up examples later. Assumptions of chi-square. As stated, the chi-square is a goodness of fit test and a test of independence. Therefore, the test does not command many of the usual assumptions that statistical tests are based on. Some of the assumptions required for the chi-square test are: First, it is assumed that random sampling is used to collect the samples from populations about which inference is to be made, and the observations are assumed to be independent of each other. This means that per subject there should be only one observation. It is assumed that in repeated experiments, the observed frequencies will be normally distributed about the expected frequencies. The goodness of fit test. The goodness of fit test is applied to a single nominal variable and determines whether the frequencies we observe in k categories fit what we might expect. The goodness of fit test can be applied with equal or proportional expected frequencies. Equal expected frequencies are computed by dividing the number of subjects n by the number of categories k in the variable. The computed value of chi-square is compared to the appropriate critical value using alpha and degrees of freedom. The critical value is found in the chi-square table available in statistics books. The chi-square test of independence. The test of independence analyzes the relationship between two nominal variables. The procedure uses the special terms independent to mean not related and not independent to mean related. The two nominal variables form a contingency table of cells. The effect size of the chi-square is phi coefficient. This gives the degree of association of the nominal variables. The phi coefficient can be obtained by dividing the chi-square of the sample with the sample size. The value ranges from a minimum of 0 to a maximum of 1. The phi coefficient of 0.5 according to Cohen 1988 convention is high, which means that researcher can have confidence that the results are reliable and can be used for population predictions. Let us take up an example considering 5 flavors of a chips brand being equally preferred by consumers. We are hence exploring the possibility that there are an equal proportion of individuals that prefer each flavor, that is 1 upon 5. Therefore, the null hypothesis P1 equal to P2 equal to P3 equal to P4 equal to P5 is equal to 1 upon 5. The alternate hypothesis is simply that the null hypothesis is not true. Suppose we select 125 subjects to represent the entire population of consumers and the observed frequencies of preference are shown in the table below. For the 5 flavors 1, 2, 3, 4 and 5, the observed frequencies are 21, 30, 24, 28 and 22, whereas the expected frequency is 25. Because the expected frequency is obtained by 1 upon 5 multiplied by 125 the sample size, which makes it to be 25. Let us apply the chi-square formula to it, and after the mathematical operations we arrive at the chi-square value of 2.4 here. The value calculated above is compared with the critical value of chi-square. The critical values of chi-square can be taken from the statistical tables available for the purpose. The table gives the probability of exceeding the critical values, sometimes referred to as the table values also, of the chi-square for the specified number of degrees of freedom. It is readily available in most of the statistics books, and if the chi-square calculated is greater than the chi-square critical, then the null hypothesis is rejected and one may conclude that the probability of equal observed frequencies is wrong. The fairness of dice example will illustrate it further. A 6-sided dice is thrown 60 times. The number of times it lands with 1, 2, 3, 4, 5 and 6 face up is 5, 8, 9, 8, 10 and 20 respectively. If the dice is biased according to the Pearson's chi-square test at a significance level of 0.95% and 99%, n is 6 as there are 6 possible outcomes 1 to 6, the null hypothesis is that the dice is unbiased and hence each number is expected to occur the same number of times. In this case 60 upon n, that is 10 times each number should occur. The outcomes have been tabulated and shown in the table. The chances of occurrence of 1, 2, 3, 4, 5 and 6 as sides have been shown in the observation column, that is the second column. We can see the observed frequencies to be 5, 8, 9, 8, 10 and 20, whereas the expected frequencies should have been same, that is 10 for each of the 6. The difference of the observed and expected frequencies are shown in the next column and the same are squared in the next. The squared difference of the observed and expected frequencies is divided by the expected frequencies, the sum of which turns out to be 13.4, which is the chi-square. The number of degrees of freedom here is n minus 1, that is 5, n being 6. The upper tail critical values of chi-square distribution table gives a critical value of 11.070 at 95% significance level. As the chi-square statistic calculated by us of 13.4 exceeds this critical value, we reject the null hypothesis and conclude that the dye is biased at 95% significance level. Let us see what happens at the 99% significance level now. The critical value is 15.086 from the table. As the chi-square statistic calculated by us does not exceed this value, we fail to reject the null hypothesis and thus conclude that there is insufficient evidence to show that the dye is biased at 99% significance level. The goodness of fit. For example, to test the hypothesis that a random sample of 100 people has been drawn from a population in which men and women are equal in frequency, the observed number of men and women would be compared to the theoretical frequencies of 50 men and 50 women. If there were 44 men in the sample and 56 women, then chi-square on application of the formula turns out to be 1.44. If the null hypothesis is true, that is men and women are chosen with equal probability, the test statistic will be drawn from a chi-square distribution with 1 degree of freedom because of the male frequency is known and then the female frequency is determined. The table gives the critical values of the chi-square. The consultation of the chi-square distribution for 1 degree of freedom shows that the probability of observing this difference or a more extreme difference than this, if men and women are equally numerous in the population, is approximately 0.23. This probability is higher than conventional criteria for statistical significance at 0.01 or 0.05. So, normally we would not reject the null hypothesis that the number of men in the population is the same as the number of women. That is, we would consider our sample within the range of what we had expected for a 50-50 male-female ratio. Let us learn to read the chi-square table and the critical values from there. To determine the critical value, we need to first find out the degree of freedom, that is the DF. For problems pertaining to chi-square, the degree of freedom will be C-1, where C is categories. So, in the above example, DF comes out to be 5-1 equal to 4. Considering this value, we find that the critical value is 9.49 when alpha equal to 0.05 and 13.28 when alpha equal to 0.01. The chi-square calculated is therefore lesser than chi-square critical, which means that the null hypothesis is not rejected. In other words, the differences in the frequency of occurrence in the observed data can be attributed to chance errors rather than experimental errors. The hypothesis testing in the case of only two categories. When there are only two categories, that is when DF equal to 1, our chi-square test is seen as a test about a single proportion. Suppose, for example, we wanted to know about the consumer's preferences among just 2 flavors of chips and not 5. We take a sample of 50 subjects, selected randomly from the population and record their preferences among these two flavors. Since there are only two categories, we may identify P as the proportion of people choosing flavor 1 and 1 minus P as the proportion of people choosing flavor 2, as shown in the table. Thus, we get the null and alternative hypothesis as HO, where P equal to 0.5, and HA, P is not equal to 0.5. Let us calculate the chi-square for this problem. On application of the formula of chi-square, we arrive at the chi-square value of 2. In this case, when df is equal to 1, chi-square becomes equal to z square. Thus, we may calculate z equal to under root of chi-square calculated and compare the value of z critical. Z is equal to under root of 2, it is equal to 1.41. Z critical is equal to 1.645 for alpha equal to 0.05 and Z critical is equal to 2.33 for alpha equal to 0.01. So, we find out that Z is lesser than Z critical for both alpha equal to 0.05 and 0.01. We would thus retain the null hypothesis for further study. When to use chi-square test? The hypothesis predicts a difference between two conditions or an association between variables. The set of data must be independent and no individual should have a score in more than one cell. The data are in frequencies, that is nominal, and frequencies must not be percentages. Lewis and Baker 1949 discussed the common errors that may crop up in the application of chi-square test to research. One of the commonly occurring error is very low expected frequency. The reasonable expected frequency in a chi-square table was recommended to be at least 10 by the authors. Generally, the test is unreliable when the expected frequencies fall below 5 in any cell. You need at least 20 participants for a 2×2 contingency table. Low expected frequencies result in type 1 errors and also reduce the power of a test. To summarize, the statistical test that is used to make inferences about frequencies is called chi-square. Chi-square is the discrepancy between observed frequencies and expected frequencies. It is used on variables that are measured on nominal scales. Pearson's chi-square test is used to assess two types of comparisons: goodness of fit test and the test of independence. A goodness of fit test establishes whether or not an observed frequency distribution differs from a theoretical distribution, whereas the test of independence assesses whether paired observations on two variables expressed in a contingency table are independent of each other, that is, polling responses from people of different nationalities to see if one's nationality is related to the response. It is assumed that in a repeated experiment, the observed frequencies will be normally distributed about the expected frequencies. When there are only two categories, that is, when degree of freedom is equal to 1, a chi-square test is seen as a test about a single proportion. In the case when df is equal to 1, chi-square becomes equal to z square.